All right, let's take a look now at an example of multiple regression. When we ran our simple regression looking at a model equation with price as our dependent variable and appraised value as our independent variable, we got an R-squared value, a goodness of fit, of 0.707. This means that there's still 30% of the variability in selling price that's not accounted for by this model equation. So we might want to consider other potential variables that could additionally explain some of that variability. And in this case, what we'll do is actually look at adding in some values that we have here for square footage and number of bedrooms to see if perhaps if we look at all of these three explanatory variables together, they may have additional explaining power in a multiple regression model. So our general multiple regression equation takes a form like this, very similar to what we saw for simple regression, except now we say y is alpha plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 and so on for every explanatory variable that we have. And of course our error term, our residuals still apply. And the betas here now are defined as the slopes for each variable under the assumption that all other variables are constant. So beta 2, for example, would be the increase in y for a unit increase in x2, assuming that all the other variables, all the other explanatory variables remain constant. So we'll calculate this model using Excel. So what we'll do is this. We're going to run the regression again. In this case, however, we're going to just include multiple variables as potential explanatory variables. So we'll go to data analysis, to regression once again, and our price is still our y value, and for our x value, we're going to actually, our x range, we're going to actually include all three of these variables: value, square footage, and number of bedrooms. And I'll go ahead and hit Control-Shift-Down arrow to complete that selection. I have included labels in those selections. I won't bother to select the residual plot, and this time I'm going to put the output on a new worksheet, just so I don't overwrite the output that we generated earlier. So Excel thinks for a while, and then it generates the following output. And it should, again, it looks very much like what we saw before, except that we now have multiple explanatory variables with coefficients showing up in our coefficient table. So first thing to look at is that, hey, we've got a higher R-squared value. We went from 0.70 to 0.77. So again, with that increase in our R-squared value is telling us that we've got, it seems at least, that we've got more of an increase in the amount of variability in selling price that we've accounted for with this now more richer model that contains more potential explanatory variables. Let's dig in a little bit more into one additional summary measure that we haven't yet considered. So otherwise, the output is exactly the same. All we saw was the larger number of explanatory variables. And I wanted to use this point to illustrate the one summary measure that we didn't talk about earlier, which is this adjusted R-squared. So it turns out that the R-squared value is going to increase once we add an additional variable, explanatory variable, into the model. Whether that variable we've added is significant or not, that's just the way the math works out. And what the adjusted R-squared does is it discounts that R-squared value to remove this inflationary effect that takes place just because we have an additional variable. And it's useful when we are using a process of developing a model by starting out with one explanatory variable and then, let's say, sequentially adding one variable at a time. And we want to compare the impact of one model versus another. Because no matter what variable we add, it's going to make it look as though the model is better because our R-squared is going to increase. But it turns out that if we look at the adjusted R-squared, the R-squared may increase with the addition of a new variable, but the adjusted R-squared may either increase or decrease. And if the adjusted R-squared decreases, it implies that the new variable we added was not significant. So for comparative purposes of one model versus another, where we're in a situation where we're incrementally adding explanatory variables, the adjusted R-squared is a very useful tool to make that comparison about the impact of the new variables that we're adding. However, when we're doing multiple regression, we still are going to use the R-squared and not the adjusted R-squared as that measure of goodness of fit. So again, here we saw that the R-squared value increased from, let's go back to our original simple regression, from 0.7077 to a new value of 0.7714. The adjusted R-squared also will have increased from 0.7057 to a 0.7667. So certainly it's showing us that we're doing something that's adding a more positive contribution. If we go down now to our coefficients, we can see that we've added, we have a coefficient for value, which again we had one before, but we now have coefficients for our two new variables that we added, square footage and number of bedrooms. We want to be careful, however, before we just take these coefficients and plug them into our equation, to make sure that each of these coefficients are significantly non-zero. So if we go to value, that may have changed, even though it was significant when it was by itself. When we put additional variables in the mix, we're creating a pretty complex model here, so things can change. So we go across from value, and the p-value for that coefficient is 6.5 by 10 to the minus 21, still extremely small compared to any reasonable significance. So that coefficient is still significantly non-zero. What about square footage? Coefficient of 2.493, and that p-value is also quite low, 2.7 by 10 to the minus 7, still much lower than 0.05. However, when we look at the third coefficient for number of bedrooms, we find it's got a negative slope of negative 1.209, but its p-value is 0.278, and that's higher than a significance of 0.05. So we would actually say this variable is not significant in our model. And what we should do, rather than just, well, certainly we don't want to include it in our model, nor do we want to just ignore it. What we really need to do is to run the model again, run the regression one more time, not including this variable that was insignificant, number of bedrooms. So now we'll go back and we'll run the regression one more time, but only including value and square footage as our potential explanatory variables. So let's do that. We'll go to data analysis, regression, and again our Y range is price, no problem there. Our input range for our X values, we're going to change that to exclude number of bedrooms. So just capture value and square footage. And I'll go ahead and put the output on yet a new worksheet. I've got labels checked, very good. And okay, and here we'll see that the coefficients for both value and square footage continue to be very significant, very low p-values. Our overall model is quite significant. And this would be what we call the most efficient model, where we're left with only coefficients that are significant, that have low p-values. Again, that's the coefficients for the slopes, for the beta values. We're not going to react really to the coefficient for the intercept, for that constant. Its p-value is high, but all that's saying is that the number is close to zero. Our anchor point for our straight line is close to zero, and that's fine. We'll just take that as it is. It's the p-values for the variable coefficients that we need to respond to very carefully. So when we take those numbers now from our Excel spreadsheet, our coefficients, we end up with this final model equation that says that price is equal to 5.5414 plus 0.6784 times the appraised value plus 2.15 times the square footage. This becomes our most efficient model. So if we had a house that was 1,650 square feet and it appraised at $142,000, we would simply plug those numbers in for the square footage and the appraised value respectively, and we would end up with a selling price that was predicted at $137,431. And again, we can apply our plus or minus based on our standard error of estimate. All right, so that's a brief example on multiple regression.